To the third lecture of ECE243. So we saw how to write our first assembly language program yesterday. And now we're going to start writing slightly more complicated ones and learning a bit more about memory. Okay, so let's start with what do you have to do for lab 1? Okay, so I mentioned the rubric is posted. You have some prep work to do. You'll get graded half on your preparation, basically knowledge of CPU later, and half on your actually knowing how to use GDB and making your program work in the lab and being able to answer questions. So go look at the rubric and get ready for lab 1. In lab 1, the program you write is to compute the sum of the first 30 integers. Okay? The first 30 whole numbers, actually. From 1 to 30. You could do this. You're all good at math. You could just do this, but you can't. You're not allowed to do that. In your head, you have to use a loop. And so far, you don't know how to do that in assembly language because we haven't shown you the instruction that's needed. So you're going to need a new kind of instruction. So you'll need something called a conditional branch. Okay, so you've already seen a type of branch or a type of jump. They mean very much the same thing. So at the end of the program that we wrote yesterday, we had this code, right? We had this label. So it means address where this instruction is placed. And we had this jump instruction. And the jump instruction said jump back to I loop. Okay, so it changed when we hit this instruction. The instruction says change your pointer program counter to this address, which is actually the same instruction. So it just kept running that instruction forever. So it's an infinite loop. And that jump instruction is what's called an unconditional jump. Okay, so it's unconditional because we don't test anything. We always do it. So this forms literally a loop, right? So we just keep going round and round and round this instruction forever. But for lab 1, I don't want an infinite loop. We're not asking you to compute the sum of all whole numbers, right? And which would take forever. We're saying we want to go from 1 to 30. So you need to repeat something a finite number of times. Okay, so a conditional branch can also change the program counter, but it checks something first, right? So it's the way we build if, then, else statements, which you've used in C. Those are actually built with conditional branches. When you compile your C code, it makes conditional branches as part of the assembly code that will implement your C program. They're also used for loops. If you make a for loop, you just have to go through 30 times, for example, there has to be a check. Have I actually gone through 30 times or not? So that also is implemented with the conditional branch instruction by G++. But now we're going to do it by hand in lab 1. Okay, so conditional branch makes a decision on what to do next. So it basically makes decisions. It checks a condition. And the condition it checks is it compares two registers. And it sees, are these two register values, are the values in these two registers equal, for example? That would be an example of a condition. So if that condition is true, then it goes to an address. Okay, and address is just a number. Here you go, well, that doesn't look like a number. Remember, the assembler is just helping us. This is just a label, which is the assembler will now figure out what address did this instruction go at, and it'll replace that label with a number. So it is just a number, but we'll often use a label to represent that number to get the next instruction. Oh, I forgot to bring chocolate bars again. So I'm getting way behind. Okay, so people are finding mistakes and I forgot chocolate bars. I apologize. So remember, if you're a person who found a mistake in the last lecture, I still owe you. I will do it. Let me ask you a question to see if you understand these labels. Okay, so the assembler clearly sees this label. Does this label, like these actual characters, do they actually show up in the machine code? What do you think? If I look at the machine code, am I going to see the ASCII characters for I, L, O, O, P in it or not? Somebody must have an opinion on this. What do you think? Yeah. Exactly, yeah. So if you look at the machine code, this is gone, okay? This is for you. It's convenience. In the machine code, you would actually see something like an address of like 0x1c. Well, let me make sure it's divisible by 4. 0x14, for example, okay? So yeah, you'll never see that in the actual machine code. It's always replaced with a number, which is the address that you wanted. Okay, so I'm going to show this with an example. So we're going to make a really simple example, which is a program that executes a loop 4 times. Okay, so we're going to make it go. We're going to make our index basically go from 1 to 4. So we're basically count from 1 to 4. Okay, so it's exactly like a do-while loop. So in C, you probably mostly used for loops. Is that right? It's probably your favorite loop. There's another loop called a do-while loop. Well, there's while loops and there's a do-while loop. A do-while loop is just like a while loop, except it checks the condition at the end. All right, turns out that when I write this, the assembly is slightly shorter if I check the condition at the end, so I'm going to check the condition at the end. I could also make a for loop, like the equivalent of a for loop if I write a little bit more assembly. But even though this loop probably is one you didn't use as often in C, where it checks the condition at the end, that's the style of loop I'm going to write. Does that make sense? But not because I can't write the other ones, just they're going to take me another line or two of assembly, and I want to keep this as short as possible. Okay, so it's like a do-while loop in C. It checks the condition at the end. Oops. Okay, so in the other section of this class, basically we're questioning whether I was really counting from 1 to 4 or 1 to 5 and whether I owed them a chocolate bar, so fair enough. So the more precise spec is 4 iterations. Okay, so I want to go through this loop 4 times. Everybody with me? Because it's a little unclear when you exit the loop if the counter is 5, did I count to 5 or not? So I want to go through this loop 4 times, and I want to at least get these integers from 1 to 4. Okay, so how does this look? So first thing I need to do is I'm going to put my loop index, which starts at 1, into a register. Okay, so move immediate, move this constant 1 into T0. Okay, so what did that do? So load immediate is move something into a register. I can't remember what I told which section. Did I tell you what immediate means? Do you remember what immediate means? Okay, immediate is assembler speak for a constant. Basically, this constant will actually be embedded in the machine code. Like it's actually going to go into the instruction. So I could actually move data from one register to another, but here I'm moving a constant to the register. It's actually a different instruction. So it's called load immediate because, yeah, I'm moving an immediate, which means a constant that gets embedded in the instruction somewhere. Okay, so that's the meaning of immediate. Okay, so this means, so in lab 1, we're asking you to comment your code. Assembly code can be all code is hard to read if you don't comment it. Assembly code, because it's so low level, is even harder. So you've got to comment it. I'm commenting this because you're learning assembly. This is not so much the type of comment. It's okay to put this comment if you want in your lab 1, but really what the comments we want are a little bit higher level. So basically, I should say something like, what am I doing with T0? So T0 is the loop index. And basically, this line is saying T0 becomes 1. Okay, so that's a bit better comment because I'm actually saying, what am I going to store here? And if you write an assembly program, because you're just using registers, if you don't kind of note what register is what, it could get very confusing. So don't do that on a piece of paper, do it in your comments. I mean, do it on a piece of paper too if you want, but don't only do that. Okay, so I've loaded in my loop index, set it to an initial value. I'm going to use T1 to be the end index, like the end condition. So I'm just going to load it. So load T1 with the number 4. And okay, so T1 is end iteration. And this line said T1 becomes 4. And let's see, I think I'm going to go over here. Okay, so now I have to write the loop. So I've kind of set things up. Okay. So in this loop, what should I do in this loop? Loop's supposed to count numbers or just go through numbers from 1 to 4. So what should I do in this loop? There's nothing really to do except one thing. Any ideas? Okay, so T0 is my current iteration count. What do I need to do in this loop? Yeah. Yeah, so I need to increment T0 or I'm not doing anything in the loop. There's no way I'm getting out of it. So let's do that. So I'm going to do add. And I'm going to do add immediate. Okay, so there's an instruction called add immediate. And let me think. We used the add instruction yesterday. This is a slightly different add instruction. The add instruction takes 3 registers, a destination and 2 sources. This takes a destination register. Okay, destination register normally comes first in RISC-V assembly. So I want the destination to be T0. I'm updating it. And I want to add 1 to it. So I want to take what's in T0 right now and add the number 1. This is a slightly different instruction than we used yesterday because I'm adding a constant, an immediate. So actually the instruction is slightly different. It's add immediate. Okay, so let's see. This is just T0 becomes T0 plus 1. And we're using this add immediate. And I want to be able to loop. So I want to be able to come back to this instruction. Right? I need to repeat this like 3 or 4 times in order to go from 1 to 4. And the instruction to do that is a branch. Okay, so I'm going to use the branch less than or equal to instruction. So all of the conditional branch instructions take 2 registers. So I want T0 and T1. It's going to compare those 2 registers. Okay? And if T0 is less than or equal to T1, then it will go to whatever address I list next. That's the third thing this instruction needs is an address. The address I want is basically the top of the loop. Go back to the add instruction. So the address I want is my loop. Okay, so what is this doing? Okay, so if T0 is less than or equal to T1, go to that my loop, or the instruction at that address. Otherwise, go to the next instruction. So you know there's this program counter. The program counter in the CPU says what's the address of the next instruction I will execute. So what this really means is the program counter is set to the address of my loop. Well, the address that is my loop. And what this one means is you just do the usual, which is the program counter becomes the program counter plus 4. Okay, so why plus 4? Does anybody know why it's plus 4? Do you remember it from our demos? So I want to go to the next instruction. Yeah. Yeah, so in RISC-V, like most processors, every instruction is 32 bits or 4 bytes. So to go to the next instruction, I have to move 4 bytes forward. So this is actually what the hardware is doing. That's what these instructions mean. And the reason this is called a branch is if you actually kind of draw where am I going, I check this condition, and I might go back there. But if the condition is not true, then I go on to the next instruction. So this is often called the control flow of a program, like what sequence of instructions are you going to execute? And this instruction produces a branch, right? So you could go this way or you could go that way. Whereas this is a very boring kind of control flow, but basically between these two instructions, it's just a straight arrow. Like everywhere where there's not a branch, your control flow is very obvious. Go to the next instruction. Wherever there's a branch, there's like a split. There's two options. Okay, and then we don't want the processor, if we ever let it go down here, and it will eventually, it just interprets what's in memory as an instruction, tries to execute it. We don't want it to go off the end of our program and start doing crazy things, so we always put this infinite loop at the end. Okay, any questions on this? Does it all look good? Okay, so everybody's with me, I think. Let me write down, put this up here. Put this up here better. Okay, the general form. Whoops. Okay, so that was branch less than or equal to, but that's not the only branch instruction we have. We have several of them. They all look like this. They all start with the letter B. They got 2 or 3 letters after that. And then they have 2 registers. Okay, so this could be any one of our 32 registers in Neos 5. And they have an address. Okay, it's the address where I have to go to if the condition is true. Okay. Okay, and dest label. Well, let's look that up for now. Okay, XX is a branch condition like, well, we just saw one of them. which was less than or equal to, but there are other ones like equal, not equal, and so on. And basically, if condition is true, the next instruction to execute is at the destination label. Right, so that means the program counter becomes the dest label. Right? Otherwise, we just do the regular instruction, which is the next one. Okay, so let me show you all of the possible comparisons. Okay, so it's branch if equal, takes two registers, takes a label. Okay, so if RA equals RB, then go to label. Right, go to just means set your program counter to that label. Okay, branch not equal, looks the same. And it's the same thing, except it's RA not equal to RB. There's a branch greater than or equal to. Okay, and that also has a label. This one does a signed comparison. And it's checking if the first thing is greater than or equal to the second thing. So RA greater than or equal to RB. And there's also a branch greater than or equal to unsigned. Okay, I'm going to stop writing all this stuff, but it's the same thing. And this is basically an unsigned comparison. Okay, so I'll talk a bit more, give an example of this in a second. But let's just get the rest of them down. So there's also a branch less than and a branch greater than. And let's see. And basically, they're the U versions of this. So we have the branch. Let's see. So we also have the unsigned versions of these. We have a branch less than unsigned and a branch greater than unsigned. And let me see if I missed any. And I guess there's a branch less than or equal to unsigned. Because I didn't write that one down here. So let me write that as well. Branch less than or equal to. Okay, so that's the complete set of comparisons that you can use. Any questions on that? Pretty clear? Okay. So let's look at why we have this unsigned and signed version. So we do have an example. Okay, so let's say I've got two registers, T0 and T1. And T0 has a 32-bit value in it, and here's the 32-bit value. Okay, and T1 has this value. Okay, which one of those two numbers is bigger? Get a 50-50 shot, even if you don't know. Okay, but we all know, everybody here remembers hexadecimal, I assume, from like 241 or something. Is that right? Anybody remember hexadecimal? Do you remember hexadecimal? You do? Good. Okay, which of these numbers is bigger? Yeah, what do you think? You think T0 is bigger? Why is T0 bigger? Got more ones? It's got all these ones up here. Okay, so you say T0 is bigger. Anybody disagree? Everybody agrees. Oh, what do you think? Right. So if I interpret this as an unsigned value, then you're exactly right. It's got all these leading ones. This is actually a very big number. So this is something like 4.29 billion. Or if I interpret it as a negative number, because in 2's complement this is actually negative, right? I have to complement it, add 1, and it turns out if I do that, that this is negative 253. Okay, this one, whether I interpret it as signed or unsigned, it has the same value, right? So this one's 2 no matter what. So in C, Python, etc., C++, you've declared a data type. Actually, in Python, you don't really declare a data type. Let's forget Python. C and C++, you declare a data type. So the compiler knows, G++ knows, what do you want? Should I treat this as a signed or an unsigned value? Assembly, you're just writing instructions. You're not declaring variables, you're not giving types, etc. You're directly working with just bits. So you have to decide, do you want these to be compared as considering them to be signed numbers or considering them to be unsigned numbers? So that's something you have to decide when you're writing an assembly language program. How do I interpret these bits? Therefore, what instructions should I use? So if I want to interpret them as unsigned values, then I would use the branch greater than. I want to figure out which one of these is bigger. Okay, so I can do that with a branch instruction, go to different code. If I want to compare them as unsigned values, I use that unsigned version of greater than. Okay. And if I want to consider them as signed values, then I leave the U off. I use branch greater than. Let's see. So which of these, is this branch going to be taken? We say a branch is taken if we actually go to the label. And we say it's not taken if it doesn't go to the label. So with these two values, is this branch going to be taken or not? I have to look at the values carefully again. Yeah, so what do you think? Is this branch going to be taken or not? Yeah. Okay, so this will be taken. So we'll take the branch to go to label. And this one is, will this one be taken too? No, so this one's not taken. So won't go to label. So yeah, this is something you have to keep track of in your programs. Which register is which variable, and also are you considering this thing? What do you think this data is? Is it a signed value, an unsigned value? Could be ASCII characters sometimes, so which is a little more handling still, but you need to keep track of that. Let's see. Okay, so let me quickly demonstrate this in Cpulator. So let's see if this is alive. Let's see if this is alive or not. Maybe I will not demonstrate this. We'll see if this works or not. It's annoying. Okay. Okay, strange. Okay, I think I'm going to go on then. Trust me, this does work, and hopefully you remember CPU later. Like practice with CPU later so that you're ready for it for your lab. But we'll just skip that because it's not working. So there's one interesting thing in the execution of this program that I was hoping to show you, but didn't work out that way. Let's see. Let me go here. So when we take this program does work. Okay, so if you actually go through CPU later, it'll properly do exactly what you expected. But one thing that's a little bit surprising is that it doesn't actually put, actually I can look at this on my screen, even though you can't see it, so I'll make sure I get it correct. So I'll make sure I get exactly what it does. Yeah. When you look at the disassembly view, so you look at what gets put, remember CPU later shows you your own source code, but it also shows you here's a disassembled view, meaning a human readable view of the actual machine code that I put in memory. And there are times when those two things are a bit different. One way they're different is I have comments in my code, so it'll show me my comments. But in this case, you actually will see a slightly different instruction when it's executing in CPU later. Instead of branch less than or equal to T0, T1, you'll actually see the disassembly view is branch greater than, and let me look at this again to make sure I don't get it wrong. Actually, it's branch greater than or equal to T1, T0, and then it'll actually have the label. And it turns out this label is at, let's see, when we actually assemble this, this label winds up being 8. Okay? So it figures out this instruction is at address 8. So you see this address 8 in memory. That makes sense, or in the instruction. But the other thing it's done is it actually hasn't used branch less than or equal to. It's used branch greater than or equal to, but it's flipped the two registers that it's comparing. First, does this do the same thing? Like, do you agree this is a legal thing to do? Is that okay? Yeah, so this actually does do the same things. I can do this. So why did it do it? The reason is this branch less than or equal to doesn't really exist in machine code. So the assembler knows this doesn't really exist. The reason it doesn't, so why does it not exist in machine code? So if you look at you're a CPU architect, okay, you look forward a few years in your career, so you're deciding what the RISC-V instruction set should look like. You only have a limited number of bits. You got 32 bits in an instruction. You could make the instruction bigger. You could make it 64 bits, but it's going to make all your programs take more memory. It's going to take longer to bring the instructions in from memory. So you really would rather not do that. So almost all processors choose to make their instructions 32 bits. In RISC-V, I actually have to go look up the exact encoding, but basically there'll be a couple of bits that say what kind of encoding are you using. So like what style of instruction is this? So maybe we've lost 2 bits for that. For this comparison instruction, I need to have 5 bits to choose the first register. Okay, anybody know why 5 bits? Why do I need 5 bits? How many registers does RISC-V or NEOS-5 have? It says 32 registers, right? So what is 2 to the 5th? It's 32. So to choose one of 32 registers, I need 5 bits. So there are 5 bits to choose the first register. There are 5 bits to choose the second register. So let me pause there and see, do you guys understand why? Does this make sense to you? Okay, remember everything that the CPU needs to do to process this instruction, like, has to be encoded in the instruction, right? The CPU will go through and figure out what to do step by step, but it has to be told everything. So it's got a couple bits saying how was this instruction encoded, like just where should I look for the registers and so on. That's just because RISC-V uses about 4 different ways to encode different classes of instructions. It has these 2 bits. It actually has to store the label, okay? It can't store the whole address. It's too big, right? The addresses, you're going to see in a minute, in Neos 5 are 32 bits. This whole thing is 32 bits. So it stores an offset. And I'd actually have to go look up how big that offset is. But I think it's 11 bits. So that's basically how much it can change the program counter by, okay? It interprets this as a 2's complement number, and we'll basically add that to the program counter. So it can branch forward or backward by about 1,000 memory addresses. And if you have to jump farther than that, then it'll do some more work. It'll have to use multiple instructions. And then there's the last, what does that leave me with? So that's like 21, 23. That leaves me with 9 bits for the operation. Which operation am I doing? Okay? Now, I'm actually just doing this off the cuff because I couldn't do my demo. So these 5s are for sure right, okay? The precise numbers for these, this could be 8 and this could be 12. Doesn't matter that much. What this means is bits are kind of a precious thing in an instruction. We don't want to waste them. So because we can actually always convert a branch less than or equal to into a branch greater than or equal to just by reversing the 2 registers that we're comparing, RISC-V just doesn't make a branch less than or equal to. They literally do not have a code in here that's assigned to that operation. And that's because they don't want to use up codes that they don't have to, because they can only, they have a limited number of operations they can encode. They're all kind of precious. They don't want to encode an operation that could have been replaced by something else. Does that make sense? Now, it could be annoying, though, to programmers to be told, you must always use branch greater than or equal to. You can never use branch less than or equal to, because the architects of RISC-V decided that this was the one they were going to make, and they weren't going to make that. So the assembler makes life a little easier for you, and it basically allows you to use either of these, and because there's just a direct, obvious way to convert this to this, it just does it. Okay, so in your source code, it's fine. Use branch less than or equal to, but you'll see this occasionally in your assembly code, like in a disassembled view, that what you see in memory is a little different than what you had. It's because of things like this, where the assembler is being clever, and the architects of RISC-V were clever, saying, I don't really need to encode both these operations. Does that make sense? Okay. Okay, so let me go on and get into memory organization. Okay, so let me just remind you of what the overall organization of pretty much any computer system looks like. There's a CPU, there's memory, and there's I/O. Okay, in Neos 5, the Neos 5 system we're using, the memory is about 1 gigabyte. And all these things are connected by this system bus. The system bus, if you actually look inside of it, it's basically got 3 things. An address, which is 32 bits. Okay, so the CPU can send out an address to the memory, say this is the data I want. It's got a data bus, which is also 32 bits. Okay, so if the CPU is reading something, that's so the memory can send back the data on the data bus. And it has a small number of control wires. So those are things like a wire that says you should be doing a read, a wire that says you should be doing a write, okay, because the memory needs to know, okay, you told me the address, but tell me what you want to do, right? I should do a read. Okay, then I'll get that data, send it out in the data bus, and the CPU will read it. NEOS 5 is a 32-bit processor. Okay, so what does that mean? It basically means two things. What makes a processor 32-bit or 64-bit, like inside your laptops, your processors are going to be 64 bits, is first the registers are 32 bits wide. And second, the address bus, right, like the size of an address, is also 32 bits. These two things basically go together. It basically, if you ever made a computer where the registers weren't big enough to store an address, it would just be kind of an insane computer. Because one of the things we're going to use registers to do is to store addresses. So nobody does that. These things always are the same. Okay, so how many locations can we select? Well, the number of combinations of 32 bits is 2 to the 32. Okay, so we can address or select 2 to the 32 locations. And almost all computers, well, basically all computers, they define a memory location to be a byte. Okay, so it's not 1 bit, it's 8 bits. Okay, so that's actually about 4 billion locations. We actually only hooked up 1 billion like memory chips that provide memory at 1 billion of those locations. That's fine. It's actually common. There's a maximum number of locations that this processor could access, but I may not need that many. I may build a cheaper computer by putting less memory in, and that's what we've done here. Okay, so then the amount of information we can access at one time. This doesn't have to be the same, but it is the same in NEOS 5. It's also 32 bits. Okay, so that's the width of this data bus, and it doesn't have to be the same as the address bus, but it is in this computer. Okay, RISC-V gives a special name to 32 bits. It calls it a word. And we give it this name because it's basically a convenient amount of data. It's the amount of data we can move to and from memory essentially as one unit. We could move everything 1 byte at a time because we have an address for every byte, but our data bus is actually 32 bits wide. So that would be a little bit wasteful, right? We would be slower than we needed to be. If we actually have larger pieces of data, like an integer is 32 bits, we can move that all at once, okay? Because our data bus is 32 bits. And our registers are 32 bits. So RISC-V calls 32 bits the word size of this processor. Okay, so we can access 32 bits at a time from memory, an entire word. And that, if we actually need a lot of data, that's the most efficient way to do it, right? Get the biggest piece of data at every time. But sometimes we want less data. Maybe we just want to change 1 byte in memory. Then we can actually also access less. So we can also access less, basically 1 byte, or 16 bits, which is 2 bytes, and that's called a half word. Okay? We're going to get, probably not this lecture, but next lecture, to the assembly language instructions that move data from the CPU and memory. And those instructions, you have to say, am I moving a word, a byte, or a half word. Okay, so that's why those sizes and those quantities matter. Okay, so I'm going to quickly go through the last thing, which is how is this laid out in memory? Okay, so here's my address. And it starts at 0. And here's my memory contents. Okay, so that's the data stored at that address. Okay, let's do a few of these. 1, 2, 3. Okay, so I put the first 8 memory locations in here. Okay, let's put some numbers in. So these are all hexadecimal data. Okay, so I've got all that memory. Every byte, every 8 bits has an address. But I can also ask for entire words. So a word is 32 bits. So this is a word. This is another word. Okay. Okay, so 4 bytes. I have to ask for it by this address, okay, if I want the whole word. I can't ask for a word by this address. And the words have to, their starting address has to be divisible by 4. Okay, so let's just look at what this looks like. So I look at that, and I interpret those 4 bytes as a word. There's a question of, well, where did you put which byte? If there's 4 bytes here, I just asked for the word starting at this address. So I know it'll be these 4 bytes. But I don't know what order it's going to put them, say, in the register inside my processor in. And the order it's going to put them in is this. 0C, 0D, 0E, and 0F. Okay, so it puts this one goes in the lowest order bit. This is the least significant bit. This is the most significant bit, right? So you change a bit up here, it's going to be billions. You change a bit down here, it's going to be 1. So that's the way that this gets arranged in your register when you bring it in. And this is at address 3, 2, 1, 0, right? So that's where I took them from. This is how they're interpreted when I bring them into the processor and load it into a register. To do the same thing here, I'm going to get, well, let's see what pattern am I going to get in my 32-bit register if I read this word? Okay, what's going to go here? So it's 4 bytes, right, or 32 bits. What 8 bits go here? What do you think? So it's any one of those AA, BB, yeah. Yeah, so it's AA. So the first one goes in the low order bits. So AA, BB, CC, DD. And yeah, this is the word at address 04. So I guess 2 things I want you to remember is first, words can only start at addresses that are divisible by 4. Okay, so the addresses are bytes. And for a word, that address has to be divisible by 4. Okay, so why do they do that? It goes to that address and data bus. If you want to, ask me after class, but basically, if we didn't enforce this constraint, we would need extra hardware and some inefficiencies when we're reading words from memory. If we, the way that memory chips work, if we enforce this constraint, everything lines up nicely, We read all 32 bits, we send them straight out to the data bus, it all works. If we allowed the processor to do things like say, let's read a word here, let's treat that as a word, it makes the hardware more complicated. There's no real reason to support that, so no modern processors do. They just, if you actually try to do this, the assembler will give you an error. It'll say, you're not allowed to do that. The other thing I'd like to note is that this pattern, where we took the lowest, the first byte, right, the one that has the same address as the word, and we put it in the low order bits, that's called little endian. Okay, so what we're doing in Neos 5 is little ending ordering. There's also big endian in some other processors. Not for this one. All that means is this is flipped. It doesn't really affect anything when you're just reading entire words because you don't really notice. You read and write entire words, you don't really exactly care what order they're put in memory. They come into the register the same way. Like they go out, they come back, it all works fine. The only time you notice is if you want to write a word and then you want to write over certain bytes inside of it, which you may do for some detailed things we do in this course, then you need to know. So we're using little endian. The only other time it matters, which we won't do in this course, is if you have two computers talking to each other or they're talking to a network. Networks also make assumptions about this. They have to all agree on what to do. It's like a really subtle bug when they start communicating integers and they like entire words and they don't agree on how to put words together from bytes. We will not make you do that. It's just something people who write really low-level software where multiple devices are talking together, it's a pain if one of them is little endian and one is big endian. For computers now, little endian dominates. So ARM, well, x86 is little endian, RISC-V is little endian, and ARM can be either, but everybody puts it in little endian mode. For networks, they actually are more big endian. So that's where there's often like a disconnect and somebody has to write some painful low-level code. But you won't have to do that. You just have to be aware of this if you ever decide to overwrite individual bytes in memory that you also want to write as words. Okay, thanks.